This is part 3 of section 4.5. The graph that I finished at the end of the last section, this is just a better version of it repeated over 3 periods. So we have our basic graphs of our 3 major functions, sine, cosine, and tangent. Now you could go through and memorize everything about our reciprocal functions, but it's not necessary. If you can graph the 3 major ones, you can graph the reciprocals. So first, let's just talk about some general properties about the graphs of reciprocal trig functions, okay? So here I've got f and g of x, and they are reciprocals. So it would be sine and cosecant, cosine and secant, cotangent, tangent, so on, okay? So if we're just talking about reciprocals of them, then these properties hold. The periods of both of them are the same. So if one has period of pi, the other one has period of pi. So if you know one, you know the other. Now zeros, these are reciprocals. So if 1 is equal to 0, then its reciprocal is something over 0, which means it does not exist. So when one of them is 0, the other is undefined, and it goes back and forth. Okay? Even and odd. If the original is even, the reciprocal is even. If the original is odd, then the reciprocal is odd. So that's the same as well. Some special values. The reciprocal of 1 is 1. The reciprocal of -1 is -1. So these are just special values. They're going to be the same right there. Okay? Now sine. If the graph of 1 is greater than 0 on a particular interval, so if it is above the x-axis on an interval, then its reciprocal is also above the x-axis on that reciprocal. So they are positive at the same places, and likewise they are negative at the same places. So if you're graphing sine and your sine graph is below the x-axis, then your cosecant graph is also going to be below the x-axis there. So all of these are fairly straightforward, and they're very similar. And you're talking about if you know something about one, then you know the other. Now, increasing and decreasing in magnitude, this is where they start to get a little bit opposite. If one of them is increasing on an interval, then the other is decreasing. Okay? If you just think about what you know about fractions, if the numerator starts going up, if the numerator starts getting larger and larger and larger, then the overall value starts getting larger. But if you take the reciprocal of it, and now your denominator is getting larger and larger and larger, then your fraction gets smaller and smaller. So where one goes up, the other goes down. Okay? And here again, this is very closely related. If the absolute value, so ignoring the negatives, if that's a small number, then f of x is going to be large. And if g of x is large, then f of x is small. So they do go back and forth. Okay? So these are the ones that are sort of opposite of each other. And the rest of these, I guess technically that one's opposite, but it comes directly from the definition of a fraction and undefined. So let's look at these graphs. Okay, so what do these things look like? If we're going to graph cosecant, okay, cosecant is the reciprocal of sine. If you look here at this graph in blue, they have our sine graph drawn. Okay? These are properties that follow directly from what we just talked about. But if we want to talk about how to get the graph of cosecant from the graph of sine, you're going to graph your sine value. And then everywhere sine crosses the x-axis, you're going to put in a vertical asymptote, because that's where cosecant is not going to exist. And then you just touch at these points that we know are the same, where you have where 1 is the reciprocal of 1, -1 is the reciprocal of -1. And they just go in opposite directions and follow along with the asymptotes. Almost exactly the same thing happens with secant. You can see here that they've graphed cosine. Okay. And then everywhere that cosine was 0, we put in a vertical asymptote because that's where secant is not going to exist. And then we touch at those special points that we know are shared, and then go off in the other direction controlled by the vertical asymptotes. Okay. Cotangent is a little bit harder to see, but it does work the same way. They've got this drawn over multiple periods here with a lot of asymptotes. But if you look at this, they've graphed tangent right here. Okay, and these two asymptotes right here, they belong to tangent. Okay, so we have tangent here, and then if you think about it, if you start repeating it on those, everywhere you would be at 0 for tangent, you're going to have a vertical asymptote for cotangent, and you can see that that happens here. This is a 0 for tangent. Even though they don't have the line drawn in, you can see that it is an asymptote for the other. Okay, and then where you have the asymptote for tangent, that's where you're 0 for the other. Okay, so they're going to cross at each other's vertical asymptotes. And we said that where one is increasing, the other is decreasing. So that's why these things get basically flipped over. Now you are, of course, allowed to memorize each graph and then talk about doing all of the shifts that we wanted you to talk about here. So if we were trying to graph this, we know how to take care of all of the shifts and the factors and the stretch and the compressing and everything. But really, it's better just to get a sketch of one of the three major functions and then use that to get the graph of the reciprocal function. So let's do an example problem here. I want to graph y equal the tangent of pi over 2. Okay, so if we want to write this, just so it's a little bit clearer, we have that. Now, if we're talking about something in this basic form here, our a value is 1. Our b value is 1/2. Our c value is 0, and our d value is 0. Vertical stretch factor is the absolute value of a, which is just 1. All right. B is 1/2. To find the period, we do pi over b. So pi over 1/2 is equal to 2 pi, which is our period. We have no phase shift and no vertical shift. Okay? So to find adjacent vertical asymptotes, we're going to take the argument and set it equal to positive and negative pi over 2. So I do x over 2 equals pi over 2, and then x over 2 equals negative pi over 2. So it's pretty easy to see that we're going to have vertical asymptotes at x equal to pi and x equal to negative pi. So let me draw those in. Okay, there's no phase shift or anything, so we're not moving things around, and tangent of 0 is 0, so I have that point there. And then we break it up into 4 equal pieces, so this one's fairly easy. That will be pi over 2 there, and this is negative pi over 2. And tangent of pi over 2 is 1. Tangent of negative pi over 2 is negative 1. So I have that basic graph. Okay. Now let's graph cotangent of pi over 2. This has the same argument as this, so I'm going to use this graph to do this one. Okay. So what do I know if I'm comparing these graphs? Well, wherever this is 0, cotangent is going to have a vertical asymptote. So I'm going to put that in here. Okay. I am going to need to find another one. Well, the period is going to be the same. So the period is 2 pi. So I'm going to have another vertical asymptote 2 pi away from here, which is actually the line that didn't print on this graph. So I'm going to sketch that in too. Okay. And now, so I have my 2 asymptotes that are going to work. This is going to be 0 where this had vertical asymptotes. So I'm going to cross here at pi. Okay. And we know on a region where one is going up, the other is going down. You can compare the regions here. So between 0 and pi, tangent is increasing. So here, cotangent will be decreasing. And it's basically the same shape, but flipped over and moved.